Hello, my name is Scott Landau, and this is the Physics 2211 lab report on the motion of a falling object. To begin, I'll introduce the lab, including the system and its surroundings. I will then analyze the shoe's motion throughout the procedure. Next, I will create a computational model to display the predicted motion of the shoe, with and without drag force. Using this, I will compare the models to the observed values. Finally, I will answer some questions related to concluding the lab. An object released from rest only has two forces acting on it. These are the force of gravity and drag force, which act in opposite directions. However, these forces do not cancel because the force of gravity is stronger than the drag force. This results in an unbalanced object, thus causing acceleration. According to Newton's second law, an object's acceleration is equal to its net force divided by mass. Since the net force is not equal to zero, there is an acceleration in the downward direction. The formulas relevant to this lab are shown below. The velocity and position update formulas are applied in the computational models to predict what the shoe's position and velocity will be as a function of time. The force due to gravity is equal to the mass times the acceleration due to gravity, or 9.81. The drag force is proportional to the square of the instantaneous velocity, and the b in this equation is the proportionality constant. These diagrams show the forces acting on the object at different times throughout this experimental procedure. First, the drag force is less than the force due to gravity, resulting in an unbalanced force in the negative direction. This is due to the shoe's velocity not reaching the terminal velocity yet. Once the shoe reaches terminal velocity, the drag force is equal to the force due to gravity, so the system is in equilibrium as shown in figure 2. This means that the object has reached and will maintain its terminal velocity. Some key assumptions made in this lab are that drag force is always proportional to the square of the velocity, and the force of gravity is constant and equal to negative 9.8 meters per second squared. I use this video and tracker technology to create a position versus time graph of the shoe position as it falls. I define up as positive and down as negative, so a downward sloping graph, position versus time graph, is produced, as seen in the top right of the screen. Note that coordinates of the graph were also provided by tracker below it. To create the computational model, I use the starter code along with the equations mentioned before. These equations are transformed into the Python commands as seen here. An excerpt of my code for the computational model without drag force is shown here. Initially, the shoe was at rest, so the position and velocity are set to 0, 0, 0. The video is filmed at 30 frames per second, so delta t is 1 over 30. V is set to 0 because drag force is not being accounted for, so the proportionality constant is 0. As seen here, the force due to gravity is calculated in the code. Since there is no drag force, the net force is equal to the weight of the box. An excerpt from the code with the model with the drag force is shown here. A key difference in the proportionality constant is set to 0.0255, a number found through trial and error to see when the computed value is equal to the observed. Finally, another key difference is the net force now includes both the drag force and the weight. It can be seen here how the net force is equal to the difference in weight and drag force. Here's the figure that displays the results of the observed graph along with the two models. First, let's compare the observed motion to the computational model without drag. Almost immediately, the model begins over-predicting the distance compared to the actual observed motion. This trend continues throughout the graph. This can be explained through the absence of a drag force because the negative net force is much larger in the model than in the observed motion. Next, let's compare the observed motion to the model with drag force. Initially, the model begins on the same path as the one without drag force, over-predicting the expected motion. However, as the graph continues, the model ends up in the same position as the observed motion in the end. A possible explanation for this is that the drag force is greater than expected in the beginning of the procedure. As the shoe rotated while falling, it became more aerodynamic, thus decreasing the impact of the drag force. A possible improvement of this lab is one that more accurately calculates the drag force of an object because the model is simply the baseline for the estimated drag force. Also, a spherical or square-shaped object can be used to maintain a constant impact of the drag force on the object rather than the object rotating while falling. Now I'll answer some relevant questions for the lab. First, which of the models predicted a terminal velocity? To reach the terminal velocity, the drag force must equal the weight of the object. The first model does not account for drag force, so only the second model reaches the terminal velocity. Next, what if the object was initially thrown downwards? If this is the case, the object's terminal velocity would not change. Terminal velocity is based solely on the velocity needed to have drag force equal to the weight of the object, so the initial velocity is not a factor at all. Thank you for listening to this presentation.